the snippet on Charlotte. And so now we're really excited for her to be able to tell you about all of her amazing research going forward. And so with that, I really want to introduce you all to Charlotte so she can tell you about the effects of spinal stimulation on neuromechanics of gait for children with cerebral palsy. So Charlotte, all yours.
And Mehmet made it. Awesome. Yes. Yes, awesome. Well, thank you everyone for being here, and thank you, Kat, for that lovely introduction to the past 5 years. I'll go ahead and jump right in and talk about how important mobility is to all aspects of our daily life. It changes as we age as well and looks different for each individual. It's particularly important though for young children as they develop, and mobility can really impact how they interact with peers, develop friendships, and gain independence. For children with cerebral palsy, though, this development can look a little bit different because of a brain injury around the time of birth that affects the input from the brain into the spinal cord and the rest of the neuromuscular system throughout development. This brain injury can cause many different neurophysiological and structural changes. One of those is an increased or hyperactive stretch reflex. This can manifest in children with CP as spasticity or velocity-dependent stretch reflex movement, where the more they try to lengthen, elongate their muscles, the more it can resist that motion. This affects about 85% of children with cerebral palsy. These combined factors can also lead to reduced motor control and reduced sensory integration. We can quantify this in movement, such as looking at intra and interlimb coordination with walking patterns for children who are ambulatory, and looking at like muscle activity. We see like increased co-contraction muscles that should be working together. Two common characteristics of CP walking are crouch gait, where they're lower to the ground with a hyperflexed hip and knee, or equinus gait, where they're up on their toes walking. And I'll talk more about those later. All of these factors can really limit mobility during these critical periods for neurodevelopment and affect the brain and spinal cord in the process. And one aspect of this is reduced sensory integration. We know from many different studies that sensory information is important for neuroplasticity, or the development of our brain and spinal cord again, as we learn and grow. As a result, there are many physical therapy interventions or medical treatments that target sensory and motor integration for children with CP. One of the big ones is physical therapy, which many of you might be familiar with, involves different repetitive activities to target learning new practices. And usually this is activity-specific training with lots of repetition and functional movements that are founded in the ideas of neuroplasticity, or learning a particular movement that can translate to daily life. Other interventions that target sensory motor integration are a little bit more invasive, like medication or injections, as well as neurosurgeries that block the sensory pathways that are hyperactive and cause things like spasticity. These are really effective for reducing spasticity, but they can also have negative effects on walking function because children kind of learn to rely on that spasticity. That and these interventions aren't specific as to what sensory pathways they're blocking. So you're losing both the hyperactive part and the part that you need to learn how to move and walk. This calls for a need for more non-invasive methods that can address both the voluntary aspects of sensory integration, such as like movement and walking, as well as those kind of involuntary aspects of sensory integration, like spasticity. This brings me to neuromodulation, which is a term used to refer to a variety of techniques that target electrical activity throughout the central nervous system. And I'm going to talk specifically today about transcutaneous spinal cord stimulation, or TSCS for short. This is a non-invasive technique that can stimulate specific regions of the spinal cord and may affect both excitability in the brain and the spinal cord. Through several modeling work and animal studies, it's hypothesized throughout the field that spinal stimulation targets the 1A afferent pathways. What that means for those who aren't neuroscientists in the room, those are, again, those sensory pathways that come from our muscles and go into our spinal cord. And those are the pathways affected or used both with movement and spasticity. With repeated use, it's hypothesized that this amplification of sensory information in those 1A afferent pathways can result in Hebbian plasticity, which is the concept that cells that fire together wire together. The more those sensory and motor pathways fire together, the stronger those connections become. It can help us kind of organize that idea of neuroplasticity. We use spinal stimulation over repeated use with sensory feedback, it's hypothesized that this is kind of again amplifying the error feedback recognition. For my control system people in there, you can think about this in a control system, amplifying feedback, which then prompts more input or control from our control system, or our brain in this case, and spinal cord, and then results in a more refined control of motor pathways. And this has been shown quite extensively in people with spinal cord injury, as well as with some invasive forms of spinal cord stimulation. But again, today I'm going to focus on this non-invasive method, transcutaneous spinal cord stimulation, or TSCS for short. Throughout my PhD, I've used a device called SCONE from a company, Spinex, where we apply stimulation to the lower back during physical therapy activities to amplify that sensory activity in the leg muscles as we're performing some sort of lower extremity therapy. This device is unique and novel because it has a 10 kilohertz carrier frequency that can suppress the pain that we feel on the surface of the skin, such that we can reach higher amplitudes without discomfort. So we're getting deeper into the spinal cord without discomfort. And this device has been explored really minimally in children with CP. And I'll talk about a couple studies that were coming out right around the time I started my PhD and the work I'm presenting on today. The first is a study that used spinal stimulation in just one about 30-minute session for children with CP and quantified some changes in the inter and interlimb coordination at the hip and the knee, as well as reductions in muscle co-contraction. So this plot on the bottom right is demonstrating a little bit of what that looks like. The top column are hip kinematics, and then the bottom plots are that muscle activity, where you can see some co-activation. He's not really able to create a stepping pattern there on the left. On the right, though, he's able to generate a stepping pattern with the stimulation. I'm actually going to show a video of him, which any of you see me present. I love showing this video because it's a 2.5-year-old receiving spinal stimulation for the first time, a few minutes taken after each other. On the left, you'll see again, he's not really able to create a stepping pattern, but on the right, we see this kind of like reflex stepping as he walks. It'll come back. And he looks really happy there to see that stepping pattern on the right. This is again just one session of simulation, and it's a very like reflexive stepping, which is potentially because we're just activating that sensory pathway in that initial session and getting some coordination output in the spinal cord. But with repeated use, again, we may be able to kind of train the brain and spinal cord to help reorganize and generate this movement on its own with the removal of the spinal cord stimulation. Upon starting my PhD, there was one study that had used multiple spinal stimulation over multiple sessions. They used it in conjunction with a body weight support system, shown on the bottom right, and they did observe some reductions in co-contraction, improvements in maximum voluntary contraction, which is how much force output you can do at the joint level, as well as improvements in gross motor function like rolling, crawling, standing, things like that. But there are some gaps in our understanding of translating spinal cord stimulation to clinical setting for children with CP. One key aspect is that studies typically look at one aspect of the effective spinal cord stimulation. We don't have a good concept of the translation of this from body function and structure up to activity and participation. So we want to understand body function and structure because this is mechanistically telling us what's happening, but it's also really important if this actually translates to improving the community mobility, because that's what we ultimately want. We've also not yet at this point hadn't seen any studies that had done a follow-up period, like how long are these changes actually sustained after they end the intervention. Ideally, you could have your intervention, it would last after, you don't have to keep coming back. And we're also still really understanding how to optimize therapy, specifically spinal cord stimulation, for each individual person, and understanding why do we have variability in some of these responses, responder, non-responder aspects like that. This brings me to my dissertation. I'm going to give a little overview of the 3 aims, and then I'll dive into them. The first aim is a clinical and biomechanical aim that focuses on using spinal cord stimulation in conjunction with short burst interval locomotor treadmill training, or SBLTT for short. This was a long study with 4 participants, and it has resulted in 2 publications that are in review. The second aim is a machine learning approach to applying a machine learning and causal modeling paradigm to see if we can quantify these individual rehabilitation responses and better understand if I modulate one aspect of physical therapy, what's that resulting effect on their outcome. This has resulted in one paper that is in preparation, very soon to be submitted. And the third aim combines spinal stimulation with a resistive exoskeleton because this exoskeleton has been shown to improve function for children with CP by targeting specific muscles. And we want to better understand how can we pair these multiple interventions together to amplify response, again, resulting in one publication that is still in preparation. All right, so that brings me back to that first aim, again, quantifying the effects of spinal cord stimulation with this short burst interval locomotor treadmill training on spasticity, walking function, and neuromechanics. I also want to take a moment to give a shout out to my amazing collaborators on this project, especially City, as Kat mentioned earlier, has been an amazing partner with me running these AMP Lab sessions throughout the past 5 years at this point. So this AIM had 4 participants. It is preliminary data that we've collected here, but I'll talk about how this has been really important though in the field. We've had 4 children in this study, ages 4 to 13 years old, all with spastic CP, and they were all ambulatory children with CP. So I mentioned their GMFCS level on the right, which stands for Gross Motor Function Classification System, 1 and 2. This scale goes from 1 to 5. A 1 or 2 is someone who's ambulatory but may need some support, and up to a 5 is someone who is non-ambulatory, requires powered mobility for movement. Most of my studies involve walking, so we work with children who have some walking ability, those lower numbers. Each participant in this study was involved for 10 to 12 months, where they received 24 sessions of SPLTT on its own, followed by an 8-week follow-up period, and then 24 sessions of that same treadmill training combined with the spinal stimulation. And we applied spinal stimulation to the lumbar thoracic region of the spine, again, where those lower extremity muscles innervate into the spinal cord. And we quantified changes in our outcomes before and after each intervention and at that 8-week follow-up period. A little bit about our treadmill training protocol. It's a 30-minute treadmill training where every 30 seconds they alternate between a slow speed and a fast speed. And that slow speed is kept consistent throughout the study, but the fast speed is increased within and between sessions to increase exertion and keep them challenged throughout the study, with the goal of increasing speed and step length over time. So our goal with this protocol is to quantify how spinal cord stimulation and SPLTT affect spasticity and neuromechanics in children with CP. We have several outcomes, so I'm going to use this little diagram to loop you back in every now and again. Our primary outcomes are these clinical measures of spasticity and walking capacity. And then we have some secondary outcomes, including the kinematics, muscle activity, and some subjective questionnaires giving feedback from the families. That slide's up there twice, we'll skip that. So for spasticity, we use the modified Ashworth to assess spasticity. This is a clinical measure where the clinician moves the joint through a range of motion and feels the resistance at the joint level. A value of 0 indicates no spasticity, no resistance. A value of 5 indicates resistance in the immobile joint. So we'll see our participants have some spasticity at baseline. That does improve slightly with SPLTT, but it goes almost back to baseline at the follow-up period. With spinal stimulation, though, we actually see a 2 to 3 times greater reduction in spasticity, which remains relatively low at that 8-week follow-up period. This is really exciting because this level of spasticity reduction is not achievable through non-invasive means in the current clinical atmosphere. It's actually not even quantified usually with rehab outcomes because it's not even expected to change. So this is huge. And we actually had some anecdotal feedback from families and clinicians as well, such as one participant's parents reporting he was able to sleep through the night for the first time because he wasn't in pain anymore during that portion of the study. Another participant was also taking medication for spasticity prior to the study. He weaned off in order to be eligible for the study. And after his follow-up visit with his doctor, they recommended he could stay off it for 6 more months because his spasticity had not come back. So again, these are just really exciting, meaningful outcomes. What's important, though, is to consider walking function in the context of spasticity. Because as I mentioned, often when we have this decline in walking and spasticity, we see a decline in walking function. So showing here on the right is a 1-minute walk test, which is an endurance assessment where they walk for 1 minute and we see how far can they walk. Again, another clinical assessment that can be repeated in a clinical setting. Excitingly, we saw no reductions in walking function with this spinal cord stimulation. It was maintained throughout the study and even improved over the duration of the study. So again, bringing back to our outcomes here, we saw these huge reductions in spasticity and maintenance of walking function throughout the study. Since starting this project, we have had some additional literature come out. So I just want to emphasize another study that looked at gross motor function in 16 children with CP, and they did report changes in spasticity. Interestingly, though, they saw improvements only at the higher GMFCS levels, not for the children of GMFCS level 1s and 2s. We're not sure exactly why they said it could have to do with the intervention itself, since again, we were doing this SPLTT, whereas they were doing another type of physical therapy. They do include an 8-week follow-up and see some similar sustained improvements. So now I'm going to jump into some of the kinematic outcomes and changes in muscle activity. With our changes in spasticity, well, at the beginning of the study, all 4 participants walked with crouch gait, where the hip and knee are flexed lower to the ground, as demonstrated in the diagram on the left here. And with these improvements in spasticity, we hypothesized that we would see improvements at the hip and knee with more extension, able to come into a more upright posture. And this is ideal because it can reduce some of the demand on muscles and lead to a less fatiguing gait pattern. So here are joint kinematics for one of the participants in the study as a sample. On the left are his hip kinematics, and on the right are his knee kinematics. And it's again over percent of the gait cycle, where 0 to 60 is stance. And that's the special part of the gait cycle where you hope to see more extension while walking. And just as on the reminder on the right, a higher number means more flex, which is not what we want, where the more extended value lower is what we do want. And we do see some improvements primarily at the knee with just the SBLTT training. But when we get to that 8-week follow-ups, it kind of goes back to baseline, even with the hip getting a little bit more flex. With the combination of spinal stim with SPLTT, though, we again see these improvements at both the hip and knee with increased extension, and these are maintained at that 8-week follow-up. We also did a statistical parametric mapping of this, which allows us to look at the significant difference across the gait cycle for each individual person. So I'm going to add those bars here, which show either significant increase or significant decrease on the bottom. And I want to point you to the dashed and solid orange lines on the bottom, showing that after receiving the spinal stimulation, he had significant improvements throughout the gait cycle with more extension at the hip and the knee. This is pulling in, so that was just an example. I did want to pull in a little bit about all 4 participants. They're showing their change in joint kinematics during each phase of the study. And again, excitingly, we see these improvements in extension, especially relative to the SPLTT only portion of the study. So I mentioned that a pattern like this can also reduce some of the demand on muscles. So we also quantified the muscle activity while performing these tasks. On the left here is just showing like a demonstration of what muscle activity looks like once you've done some filtering, if you're curious. Again, over percent of the gait cycle, with the top row being vastus medialis, that's one of your quadricep muscles, and the bottom being the medial gastroc, one of your calf muscles or plantar flexors on the back. We especially care about these again during stance. Usually they're in high demand during stance because of CP, because of that crouch gait pattern. And so I'm showing changes in these average values, again, after SPLTT only and after spinal stim combined with SPLTT. And we see improvements, especially up at the quadriceps, of reductions in this integrated area with spinal stimulation. That was also present when we look at co-contraction of the antagonistic muscle. We saw less changes at the ankle, and this may be because during SPLTT they're wearing some rigid braces or whatever community mobility aid they use in the community. So this might be affecting something to consider when we think about implementing spinal stimulation. So we saw these improvements in kinematics and muscle activity, which gets a little bit more at that structure function, but we also want to translate to how it's affecting their community mobility and daily life. So I'll show a couple outcomes we have here, but this work is ongoing for us. One of these is fatigue, quantified via a self-reported measure where we asked either the parent or the child to tell us about their fatigue in daily life, and it's a scoring-based system. And we saw increases in fatigue reported in community walking after SPLTT only, but it remained the same or actually decreased with the spinal stimulation, kind of paralleling what we were seeing with the muscle activity in the lab. We also asked them about their movement goals through a questionnaire called GOAL, Gait Outcomes Assessment List, where this asked them a variety of questions around their gait appearance, their mobility in daily life, how they're able to do things like sports or interact with their peers. And once again, we see improvements after the spinal stimulation, especially compared to what we see in changes with just the SPLTT on its own. So we have this small sample size of 4 people, but exciting to see these consistent improvements across individuals. Again, I want to pull up another paper that has come out since our starting this work that looked at changes in gross motor function as well as quality of life in 16 sessions of the spinal cord stimulation. And they did also report improvements in motor function and quality of life, kind of similar to some of these subjective questionnaires we've reported here. So this aim one of my PhD has been the first study to examine the effects of combined spinal cord stimulation with SPLTT across clinical, functional, and biomechanical assessments. We've also, one of the first groups, to measure these sustained improvements up to 8 weeks after the intervention. And we think, there's justification to go even further than that because we aren't seeing that decline after 8 weeks. And also really excitingly, this pilot work of 4 individuals has allowed us to apply for an NIH R01 grant that, if granted, will be a similar protocol with some blinding for participants and will allow us to implement spinal stimulation in a research setting for 56 children in the greater Seattle area. So stay tuned for more about that. This brings me to the second aim of my PhD, where I kind of hinted at this, but we see some different responses between studies within our own studies to these interventions. And this is a challenge not just with spinal stimulation, but across rehabilitation interventions of how do we optimize the care that we're giving to the individual person and then track that progress over time. And so again, I would like to thank my amazing collaborators for our work on this project. And I'm going to go back to our SPLTT intervention for this. And SPLTT has been shown to be effective for children with CP because it affects speed modulation strategies, but we haven't yet actually quantified what does that mean exactly. So children with CP have reduced step lengths and increased step widths compared to their peers. And these are thought to be contributing factors for reduced stability during walking, reduced energy efficiency, and reduced interaction with their peers. And so SPLTT has this goal to target improved step length specifically, especially at those fast speeds, but we haven't yet been able to quantify this in kids with CP. So for the second aim of my study, I used data that we collected during aim 1 with just the SPLTT only, and we recorded pressure data from a treadmill while they were training with SPLTT in 5 sessions of those 24 sessions I reported on. And from these center of pressure information, we're able to get outcomes like step length, width, and asymmetry. And so, like I mentioned, some of our clinical partners are interested in understanding how SPLTT affects step length. And to think about these relationships, I'm going to draw a causal diagram where my outcome that I'm targeted understanding is step length on the right, and my exposure or treatment I want to look at is at SPLTT. So we want to understand the effect of SPLTT progression on step length, or you could do this for any outcome demonstrated on the right. But there are other factors that change with SPLTT that could also influence step length. These include things like treadmill speed. Again, that's changing within and between sessions to increase exertion. We also sometimes modulate the treadmill incline to prevent them from running, to keep them walking. And the time within session can also affect step length. If they're fatiguing, for example, they may reduce their step length with time. Traditional methods for quantifying changes in rehab protocol would involve a sort of total effect, as I'll refer to it, looking at what is the effect of SPLTT on step length, despite all these factors that are also changing. This might look something like this on the left, where I'm showing just each individual participant's change in step length from the first to last session of SPLTT. But I have not yet accounted for what I showed you there in my causal diagram of speed, incline, time in session, or even side of the body. For example, I'm showing the change in speed on the bottom right there, where we see this increase in speed with time. It looks linear, but that's because we're only plotting the first and last session. In actuality, a lot of these relationships are nonlinear. There's inherent variability within and between participants, and there's an interaction, as I demonstrate here with my causal diagram, between variables. And so this has been a challenge with methods thus far that are available for us for quantifying outcomes. And so this aim is focused on understanding if we can use machine learning and causal modeling to quantify the direct effects of SPLTT on step length. My example will be SPLTT on step length, but with the idea that we could apply this to several rehab paradigms. The machine learning tool that I use here is Bayesian additive regression trees, or BART for short. This uses Bayesian probability and a regression tree, as demonstrated here on the far right, to make decisions between my inputs into my model and my outcomes. So for example, it would set decisions based off my model inputs I showed in my diagram, like session number or speed, and then our outcome would be step length, and it's classifying those step lengths based on the inputs I give it. This allows it to handle, again, those nonlinearities in the data. And so far, BART has been used in several applications, including CP to focus on predicting responses to rehab, as well as understanding increases in metabolic power and predict responses to gait training. These have all been across like a group-wide outcome though. BART has yet to be used on an individual basis to track progression over time. So I'm pulling back up that total effects plot here, which is just our pre-post change in step length with SPLTT. And now I've added in the direct effects plot. This is what I get from BART. This is a accumulated local effect, or ALE plot, where it shows the change of my outcome, step length, with change in session number, while controlling for all their inputs into my model. And as you can see, the relationship here looks quite a bit different from what we were seeing pre-post on the left with total effects. Even one participant actually declines with session number, which I'll talk about in a little bit. Because this ALE plot generates the outcome with respect to each individual input to my model, I can actually generate this for every input in my model and understand a variety of relationships. So I'm just going to demonstrate that here real quick. With speed, as we see, there's a strong positive relationship between speed and step length, as well as time in session, the affected side versus left versus right, and incline for the two participants that did use an incline. One thing that's really important when we're looking at any sort of machine learning model is model fit. So I've added here the model fit reported as R squared and the age and years of each participant. In general, a value closer to 1 for R squared is much better. So you'll see for our 4-year-old participant, we actually have a really low R squared, which I will get to. But looking at this data and applying this application, we wanted a way to actually validate that BART is getting me the result that I expect. Is it accurately giving me out the relationship that we put into it? So to do this, we developed a virtual data set of 150 participants where we base step length progression off these 4 participants to keep it in physiologically possible ranges, and created normal distributions of step length progression with early starting speed, change in speed within and between sessions, as well as like time in session, that fatigue aspect, and generated this huge data set where then put it through BART and to see if BART could then pull out the relationship I had put it into the model. And there's 3 questions I'm going to answer using this data set. The first one is BART actually able to predict the response accurately? Is the model the input I specify what BART's able to pull out? To do this, again, I had that generated data set where I gave it a specified step length or kind of rate of change of step length between sessions, and then used BART and the ALE plot to get a predicted rate of step length. Excitingly, across these 3 participants, when I looked at the change in specified step length on the bottom axis with the predicted change in step length from BART on the vertical axis, we see a strong correlation between these two, suggesting that BART is able to accurately predict step length progression. Now I want to get a little bit into some of the challenges we have in rehab and how can BART handle those challenges. The first thing is, again, this low R squared we saw here in our young 4-year-old. If you've ever watched a 4-year-old walk, it's not very consistent. There's a lot of variability in how they're stepping. And so we wanted to know if the step-to-step variability impacts accuracy and model fit. And just to show an example, I've added the standard deviations here as well for these participants. And he has almost twice as high a standard deviation or step-to-step variability compared to the other participants in the study. And so I wanted to know if this step-to-step variability can cause a reduction in my model fit. And if it does, is my model still accurate? Is that still something I can use? As we hypothesized, we did see a reduction in variability with an increase in variability. We saw a reduction in model fit. It gets really low there with the added variability to my system. And then again, we wanted to look at this accuracy. So I keep variability on the bottom axis, but the vertical axis is the step length error. This is the error between what I specify in the model versus what my BART model is able to predict. Excitingly, though, we see no relationship between the added variability and the accuracy of the BART model. So even though this reduced model fit, it's still accurate outcome that we're getting from BART. The last thing I wanted to explore here were nonlinearities in the data. This is an example here with PO3 in the study, where I call this a plateau point. He increased step length initially, but then stops increasing throughout the study, which again, if you were a parent and your children was in a program to improve step length, you'd want to know if it's no longer progressing with session and be able to maybe adjust the therapy program, or the physical therapist might want to change the intervention. So to test this in my virtual data set. I specified a plateau point in the model and then used BART to pull out that plateau point as well. And so this looks similar to my first plot where I showed the specified plateau point in the bottom with the predicted plateau point on the vertical axis, grouped in sessions of 5, similar to how the data set was actually generated. And we see again a strong R squared across this data set, suggesting that BART was able to actually accurately predict that plateau point and handle nonlinearities in the data set. So some takeaways from this work, this causal modeling and BART paradigm were able to accurately track these individual training progressions, as we showed with that in silico data set, especially in handling the high variability and the nonlinearities we might expect to see in rehab. We also then used this application to show that SPLCT had a direct effect on increasing step length for 3 of 4 participants, but it also pulled out that one participant was maybe not having that direct increase that we thought just looking at the data with a total effect. This work has provided a novel method for tracking rehab, such as this driver of increase with step length with SPLTT, and we were able to use this in silico data set to validate some of these outcomes. This aim has been really important for tracking individual rehab progression for step length as an example, but there's other pieces of information we may want to know during a session to track progression. And one of those is muscle fatigue, which I'm going to jump into with my third aim. We're focused here on quantifying the effects of muscle fatigue when walking with spinal cord stimulation and a resistive exoskeleton. And once again, I want to thank my amazing collaborators who have worked on this project and the ongoing research, especially with this aim. Fatigue is defined as a decline in force output at the muscle level. For children with CP, they actually have a resistance to fatigue when you ask them to push as hard as they can or use that maximal effort, but the maximal effort is lower. They're not able to reach as large a force effort. But then when we look at submaximal contractions like walking or doing a squat test, children with CP actually fatigue faster. They're not able to do the task as repetitively as a peer. And this we've seen manifest in daily life with reports of reduced activity and increased fatigue from qualitative work, but it's also important to consider during physical therapy and how we want to regiment the physical therapy. This is because prior work, primarily with animal models, has shown that the level of intensity can have a direct effect on the neuroplasticity and learning happening with an intervention. So too low of an intensity is not providing enough actual challenge to the body for the learning to happen. While too high of an intensity, this overexertion can actually reduce aspects of neuroplasticity. So there's this idea that we have this kind of ideal sweet spot of moderated intensity. And this is not usually tracked in rehab programs. We may ask someone about their physical exertion or use ways to observe their function, but we don't have a strong parallel of this through actual muscle fatigue during training. And so one aspect, an example of when we may want to consider this is interventions that target increasing strength of a particular muscle. Here I'm going to talk about a resistive ankle exoskeleton, or EXO for short, that has been shown to be effective for children with CP, for improving strength, reducing metabolic costs, and other aspects like increasing walking speed and endurance, improving motor control, and reducing co-contraction. Some similar outcomes that we've seen across other studies. And this device works by actually resisting the plantar flexors during push-off of the stance phase of gait cycle. And so it's making the activity more challenging with the goal of strengthening that muscle so that when you remove the device, they're able to walk more efficiently. But so far, we haven't quantified changes in how this affects fatigue of the muscle and that engagement of the muscle directly. I've also been talking a lot about spinal cord stimulation, and I just want to recap some of those outcomes, such as improvements in co-contraction, reductions in integrated area, and reductions in self-reported fatigue. All of these suggest that spinal stimulation may have an effect on how they're activating their muscles in a way that reduces demand and reduces fatigue. So the goal of AIM 3 was to look at how spinal cord stimulation and this resistive exoskeleton affect fatigue during training with children with CP. We hypothesized that the stimulation might actually be able to reduce the impact on muscle fatigue and optimize these aspects of neuroplasticity. So I mentioned that fatigue is quantified with a reduction, or defined as a reduction in force output, but we can actually look at the muscle activity and see the onset of fatigue before it happens mechanically. This is because as our muscle starts fatiguing, we see a reduction in conduction velocity, which I can record in my EMG by looking at the median frequency of my EMG signal, which will reduce when the conduction velocity reduces, and we'll see an increase in amplitude of the EMG signal. So to quantify fatigue with this exoskeleton, we did fatigue assessments under 4 different visit types with 9 children with CP, ages 4 to 14 years old. Again, GMFCS levels 1 to 2. They came in and walked on 4 separate visit days with either no devices, just the spinal stimulation, just the exoskeleton, or the 2 combined together. And this is a demonstration of our exoskeleton with one of our participants. We recorded the maximum voluntary contraction before and after 20 minutes of walking in each of these test conditions, and recorded their force output during that task, which is basically how hard can they push their plantar flexors and what's that force output, and quantified the muscle activity with both the amplitude and that median frequency during the task. I'll show these results with some box plots. On the left is the change in force pre-post the task, and on the right upper is the change in EMG amplitude, and the bottom is the median frequency. And I have some arrows reminding you which direction indicates fatigue, because I know that gets a little bit confusing. We saw some reductions in force output with no devices. We didn't observe any changes at the EMG. With spinal stimulation, the exoskeleton, and the combination of the exo plus spinal stimulation, we didn't observe changes in force or EMG activity during the maximum voluntary contraction. And even though we saw that reduction in force with just the devices a little bit, it was not significantly different from the other tasks. So this kind of limits our understanding of what the fatigue is happening, but there are some challenges with doing maximum voluntary contraction in children with CP. In prior work, we've actually seen that children with CP cannot maximally activate their muscles. They don't have that refined motor control to push as hard as they can and activate in a way that an unimpaired child might be able to do. So while it has been used before, it's not really a good representation. We actually get more muscle activity when they're walking than when they are asked to maximally activate that muscle. The MVC is also a completely different task than the training task, so it's unclear if those changes really truly translate to how they'd be walking. And we have to stop the training assessment to actually do this assessment. We aren't able to track during the intervention itself to look at changes in fatigue while they're training. So we also applied, to address some of these concerns, we also applied our EMG assessment toolbox during the walking activity, looking at changes in amplitude and median frequency. I'll show these during 5 minutes of walking with the devices, where the top is again amplitude and the bottom is the median frequency. And we did assessment of the EMG every 15 seconds throughout the 5 minutes. And it's normalized to their value at the start. So a value of 100 indicates no change. And then past that is a % change relative to the initial. So with walking without any devices, we don't see any signs of fatigue at the muscle level. Similarly, that holds true when they walk with the spinal stimulation. However, when they walk with the exoskeleton, we see increases in fatigue at both the amplitude and the median frequency, much larger than it is without this device. Interestingly, though, when we add the spinal stimulation and use it in conjunction with the exo, we don't see that same rate of fatigue in the muscles. We do see some small increases in the amplitude of the signal, shown there on the top. It's really small. This suggests they might be actually pushing harder or engaging more with the device without actually fatiguing the muscle, because we don't see a parallel reduction in median frequency. These are all linear regressions where I show that R squared on the side. And so I'm also going to show, this is the average across participants, but I also want to show what those average rate of change or slopes of those linear regressions look like, because it was not significantly different across task groups. And I think that's largely because there's huge variability with the exo condition for the children with CP. And again, suggesting that we need to better understand how they're engaging with the device. And that could be a large cause of variability here. This project did show that the exo non-systemically increased the rate of fatigue in the first 5 minutes of walking, which is actually a good thing because it's showing that we're actually effectively targeting that muscle. But maybe for rehab and implementation, we may need to consider duration of training or intensity to maximize the outcomes. We also saw that the spinal stimulation may be able to protect against that fatigue, again, maybe helping us optimize the implementation of that device. And quantifying this fatigue during walking may give us more insight than the pre-post assessments and the limitations we saw there. This is the first study to look at fatigue with spinal stimulation or the exoskeleton, but we've seen a lot of evidence in other models that we should consider this with dosing. It also demonstrated the effectiveness of the exo in engaging those plantar flexors and we're able to compare the different methods of quantifying muscle fatigue. So this brings me back to the dissertation outline, the 3 aims I've talked about today. In addition to the publications I mentioned that have resulted from their work, we've seen some clinical and scientific impact from each of these that I'll jump into a little bit. The first aim was the first study to look at mechanistically at the effects of spinal stimulation across both spasticity, kinematics, and movement, as well as translation to some community mobility. And really excitingly, we've seen these huge improvements in spasticity, warranting some further research into understanding these mechanisms and if this holds across a larger group of individuals. With AIM 2, we validated this machine learning model for individualized tracking of rehabilitation. This has been an important scientific impact, but also clinically, we hope to apply this in the future for tracking progression during rehab and understanding drivers of change. So you could go into a session and actually understand what I'm adjusting during therapy and what's that direct effect outcome on our targeted rehab goals. And finally, with AIM 3, we have quantified this fatigue during tasks and across tasks. And the evidence we found here suggests that spinal stimulation may be able to protect against fatigue, allowing for some more optimal kind of conditions for that neuroplasticity when we apply it with these more challenging training activities. In addition to these kind of broader impacts, I want to take us a moment to note some comments from some of our families in qualitative interviews that we performed. Some of them have also, in just one session while observing their child's walking, have noted improvements in just one session. These are, parents who are observing them every day, and so seeing a change in just one session is exciting. One parent reported, with stimulation, her walking is very close to normal. It made me feel like a dream. She felt strong, stable, and confident. Families have also reported that they are hopeful and willing to try these interventions. For example, again, with the spinal stimulation, one parent reported, I would hope it would help him make the neural connections and keep him out of surgeries. Again, this idea that we want these more non-invasive approaches that can translate to both spasticity, walking function, and community mobility. I think there's a lot of future work that I will just touch a little bit on here. For one, we've been focused on the biomechanical and functional changes, but I think it'd be great to go even deeper into the neuroanatomy and neurophysiology to understand what's happening deeper mechanistically to each individual person. We've also demonstrated the example of using BART and causal modeling for tracking the SPLCT progression, but I think we can also use it in aspects like fatigue, like I showed here. How can we understand what's driving fatigue and use that to modulate different sessions, such as change in input from a physical therapist, like audiovisual feedback, or how often to implement rest breaks. And we've started doing some qualitative interviews, but we'd like to continue to do those to help understand the user interest in these devices and how we can implement what we've done in the lab into their own clinical and community mobility. These 3 areas of both the neurological mechanisms, kind of this idea of amplifying sensory feedback in rehab, as well as individualized rehabilitation, I think are all critical for helping us translate this research, particularly in spinal cord stimulation, to clinical care for children with cerebral palsy. That's the next or future work for this area, but as Kat kind of mentioned, future for me, I will be starting a postdoc this summer with Daniel Ferris at the University of Florida as part of a T32 postdoctoral fellowship in translational research in aging and mobility. And I'm going to be working with this large data set of mobile EEG data on understanding the decline of walking function in older adults. And I think this is a great, awesome area we can combine with what we've done during my PhD to better understand mobility and connecting the changes in neural activity to function. So I'd like to say thank you to my amazing mentor, Kat, and Chet, who has been also a key mentor on all these projects, as well as Chrissy Bjornson, Heather Feldner, and Desiree Roget, who have been our key kind of PIs across these projects. Of course, the Steel Lab and all of our lab support and funding organizations, and not just only the professional support, but prepare yourself for the most overwhelming slide of my dissertation. I also wanted to put up a collage of just some fun photos throughout my PhD and thank all of the people who have been supporting me along the way, both in the lab, friends, family, and faith and my dog that have been so supportive. I'm appreciative for all I've learned throughout this process, including how to make memes as demonstrated in the bottom right. There's a lot more of those if you decide you want to see them. So. Thank you for your time, and I'm happy to take questions.
All right, thank you, Charlotte. We will now take questions from the audience, and then we'll have the closed door session. So if you're online on Zoom, feel free to raise your hand and we'll call on you and you can unmute. And if you're in the room, you can raise your hand and we'll call on you. Any questions for Charlotte?
Yeah, we can see you.
Hi, as someone who's about to dive into the part for individualized rehab.
Yeah. Yeah, I'm going to repeat your question just for the Zoom audience. She asked about if considering GMFCS level might be an important consideration for BART for the individualized models. And I would say if you're going to do a model across people, definitely something to consider that like baseline function. On an individual basis, I was not something I inputted because it's a model to the person, and GMFCS level isn't something we like expect to necessarily like change with a duration of this time. So I would think like if you're building one model, it would just be the same input for all of your test conditions. I would suggest doing something like that causal modeling diagram and thinking about what outcomes might affect your response variable within participant, and then using those as your input into your BART model. Great question though. Awesome. Yeah, Heather.
Realizing that we're hearing some of the discussion in regard to aim one, with the spasticity reduction, I have never asked you what the significance is of the 8-week follow-up / washout, right? Obviously, I don't know if there's a specific like neuromodulation reason for choosing 8 weeks versus 6 or 3 or 12 or whatever. And I would love to hear more about that.
Yeah, great question. So again, I'll repeat for the audience on Zoom. Heather asked about why 8 weeks follow-up of that AIM-1 study. And that's a great question. I think there's plenty of reasons to justify a variety of durations for length outcomes. We picked 8 weeks kind of based off the prior work in spinal cord injury and what they'd seen as far as sustained outcomes. I don't show it here. We actually do 3 months follow-up, so 12 weeks after the last spinal stim visit, and we still see reductions in spasticity, kind of warranting like we need to go further. The hope, even with the SPLT and having that 8-week follow-up, is it would be enough to wash out. I believe there's been observations of SPLT improving function sustained to 6 weeks follow-up, but not 8 weeks. So yeah, it's mainly based on the prior work, but suggesting that we maybe need to go a little bit further out. Yeah. Yeah, ZG.
For your history, let's say you actually the impression of the beat using Apple and PSCS. Very way as they like, I know the Apple is supposed to kind of take those muscles, also seeing doing technique. You actually see it deeply with PSSCS response. Is there any way to tell them, are they just not getting that exercise, or they're still getting that exercise, but it's just easier for them, so it's still less? Yeah, great question. So ZG asked about the exo condition here, where we're not seeing the fatigue. So does that suggest we're not engaging the muscle appropriately? Like, is that negating the effects? I will also add, we kind of pseudo randomized these, so it wasn't like they learned exo the first time and then got spinal stim. So I do think this is actually speaking to the intervention itself as opposed to like a learning effect. And the main thing I would suggest we look at is these two outcomes together. And so, like I mentioned, there's a small increase in the amplitude of the muscle activity without the reduction in MDF, and it's really small here. They do go for 20 minutes, so we hope to look for further outcome, look further in time. That increase in amplitude without the reduction in median frequency suggests that they are increasing engagement within that 5 minutes without fatiguing. I will also add, though, I think right now I've normalized it to their start of session, but they're already walking with the exo. So this is just looking at their change from first minute to 5 minutes. We also hope to look at normalize this through their MVC task each day, which is like a control across days, but they're not in the device yet. And so that would tell us if at the first minute, are they already higher activating? The challenge we saw with that, though, is that they're not able to maximally engage in the MVC task. So it's a little bit harder to do a good comparison as well with that.
Susan Hastings asks, why did you choose the 1 minute walk test instead of the 6 minute or 12-minute walk test?
Yeah, great question about the walking test length. We actually did do 6-minute walk test for the very first participant in the study. And doing it repeatedly over and over again for this 12-year-old was just like, he was just so sick of it by the end of the study. And I think that actually maybe could have affected how well he was doing the tasks. He was getting bored. And so we chose to kind of switch to the 1-minute walk test to hopefully like make it more of a valid outcome in task and allow us to be able to get some more reliable results. We did still repeat the 1-minute walk test each visit. So they did 3 minutes walking, but in 1-minute increments. And I think that helped engagement and gave us even a little bit of repeatability within each session to make those results more reliable. But there's lots of options there for sure.
All right, if there are no further questions, going once, twice. Oh, Megan has one more.
Yeah. Okay, good question. One of the most surprising things I've learned during my PhD. I feel like there's 1,000 answers to that question. I think this is probably the cliche answer, but getting to do a lot of those in-person data collections, I learned a lot of the challenges that happen. Like as engineers, a lot of times we just get a data set and then we like apply it and we get to analyze that data set. I was really fortunate to get to do both the in-person data collection, having fun with the kids, but also trying to get them to go, walk in a straight line to the actual like a data analysis piece. So I've really enjoyed getting to do both aspects of that during my PhD. Yeah. And Elijah also raised his hand on Zoom if we have a
I'm
second.
glad you still find it as fortunate. Elijah.
Hey Charlotte, can you guys hear me?
Yep.
Yes.
Is it like Wizard of Oz kind of over the whole thing too loud?
Yeah.
Sorry.
That just happened.
Awesome job. Great to see you kind of come over to the in silico side a little bit after your long experimental run. Amazing work. Seriously, you've had some crazy amount of impact that I don't think I've seen from like any PhD. So congratulations on that. I am curious about the BART model. So a lot of what you were looking at and a lot of what you're focusing on now is kind of the neuro aspect. Do you think from the transcutaneous spinal stimulation, do you think there were any physiological changes that maybe were hidden or could be added to your model? It could be something as simple as weakness or contracture. Do you have any thoughts on that?
Yeah, especially looking like over time, there's a lot of aspects that could change with rehab. And so that's definitely one of them. We did look at like changes in muscle tendon lengths, actually. I don't show it here. And interesting, we didn't like operating muscle tendon lengths during walking. We actually didn't see a change with that across the study visits. But I think it's a balance between like how much data can we collect within a session, both in the research, but then also translating this to clinical. What can we feasibly collect that's actually important, which in a research setting, we can explore those things and hopefully narrow down that data set, maybe using modeling techniques like what you've done, and then hopefully like help that understand like what's most informative for our BART model that may impact outcome. And that could explain some of the variability in the data set that we aren't able to capture with the outcomes I've included so far.